recording. And yes, I'm now recording Planet 9 from outer space. Maybe we'll have a watch of this at an event.
Right now was the table read, then the
Yes.
movie's at like 9:30.
Very cool. Very cool. Thanks for the heads up, Steve. All right, so welcome everyone to the May virtual meeting of the astronomy section, the Rochester Academy of Science. For those of you who don't know me, my name is Mark Minerich, your president. Glad to host you this evening. Glad everybody was able to be here tonight. So lots of things happening here. First, let me thank Dave Pesch and Expudo.com for donating this service. The advantage of the service through David is that we can have any amount of people we want on here and stay on as long as we want. We're not stuck by some of the rules with some of the other services where you can only have so many people or so long where you have to pay for it, and this keeps it free for us. I'm looking at some of the people here. It looks like we might have some visitors. I did invite the folks from the Mohawk Valley Astronomical Society to join us. We may have a few of those people there, so we want to welcome you guys aboard if you're here. How this works, you actually control your muteness or not. I can actually control it too. If you end up with a hot mic, I may mute you. Please don't take that personally. You can always talk if you'd like to. Just unmute yourself. You can speak whenever you'd like. But if somebody has a hot mic, I will mute you. You can use chat for questions, and I would encourage you to do that, especially if you have questions during the main talk. Be glad to interrupt Donald if it's a pertinent clarification question. Otherwise, we'll hold questions to the end for that. All right. So here's our agenda. Welcome. We just give a welcome. I'll have a number of announcements, and then our featured talk tonight is by Donald J. Brighty. He has a PhD.
I'd like to correct one thing. I am not currently affiliated with SCO.
Okay. Yeah, I know you were before at one point in time.
Most of my career has been in either industry or in the labs, Bell Labs and MIT Lincoln Labs. So only somewhere in between do they teach at SU. So
thank you for the clarification, Donald.
Okay.
And he'll be talking about wormholes and time machines and a whole bunch of ramifications for that. So we'll look forward to that.
Should be
fun. In a few minutes. All right. So is this anybody's first time here? First time you've been at an astronomy section meeting?
Yes.
Yes, our speaker, of course. Glad to have you here. Anybody else? Howard?
Yep.
How'd you find out about us?
Oh, I've known Don for a long time, and
Okay.
I've known Ted for a long time, Ted Lechman.
Awesome. Awesome. Welcome. Glad to have you.
Thank you.
My little comic here is a XKCD comic about roommates meeting for the first time, both having the same Pink Floyd poster, and they figured out how to make it work together. Any observing recently? I took a couple of images that some of our folks took over the last month. James Canning got M81 and M82. Bob Montgomery got a nice image of the sun. Peter published a bunch of images in our on our newsletter. Anybody get out and do some imaging or just visual observing over the last month? Doesn't sound promising.
This is only partially related. Well, it is related. There was a more weather, but there was a great halo around the sun yesterday.
Yes, I saw your image online. That's beautiful. Great shot.
Yeah, it was very prominent.
I didn't catch it. I wasn't paying attention.
Well, I was outside taking a walk, so I happened to look up at the sun.
Yeah.
Otherwise, I wouldn't have noticed it.
Yeah.
Hey, this is Douglas.
Go ahead, Doug.
I saw one very big meteor Thursday morning around 5 o'clock.
Wow. What part of the sky?
It came up from the southeast horizon and went right overhead.
Oh, no kidding. So that was a pretty bright meteor then. It was going across like that. Wow.
Yep, the moon was right where it started.
No kidding. Kind of a bolide size thing, or was it a little smaller than that?
Yeah, just kind of a fireball.
Okay. Okay. That's cool to see. They're always cool to see. That's pretty awesome.
We should mention about the June 10th.
Yeah, it's coming up. It's coming up. All right. So we had a Messier Marathon in March, and then we had a rain date or a better weather date of the 10th. Did anybody go out there and try to find some of these? I recorded me doing it, and I found 106 objects and did them through 2 videos that we did for the Messier Marathon. But mine don't count because I had a tracking telescope and I could go to it and swing to it and didn't have any issues getting there. But anybody else work on the Messier during the last month or so? Hank, you went out. Hank's got his. He's not on speaker, but I know Hank was with me the first night, and he got a few. We got probably, I don't know, what'd you get there, Hank? He's typing it now, and I think he was going to head out again in April to see what else he could find. Let's see what Hank found 99 over 2 sessions. That's awesome. Man, that's hard to do. That's pretty awesome. And Hank did it the old-fashioned way. He earned it. I mean, he hopped from one to the other. Using the scope he's got. That's pretty awesome. You did this from home the second night? Star hop. Yep. That is the old-fashioned way. Nice job, Hank. That's cool. It's a fun thing to do. There's all kinds of challenges out there if you're an observer. Messier Marathon is probably the one of the simplest. And once you do the marathon once or twice, you can get pretty good at finding these things in the sky pretty naturally, a lot of the big ones. And Jim Sidewan could pretty much find any of these without even looking at the chart. Right, Jim? Anyway.
Yeah, trick is lose low power.
Yes, that's it. That's exactly it. You don't need high power to find them. Maybe to observe a little deeper, but not to find them. It's a lot easier, low power.
You can knock them off 60 seconds a piece and just.
There you go. That's it. That's it. I released a number of talks. I know Carol shared some of these too. Did anybody catch any of these talks? These are the ones in the last couple of weeks. There were some that were really technical that I didn't forward on. I mean, and if you guys want the real technical stuff, I can forward those on to you too. But I saw a couple of these. I thought they were pretty good. The first guy on April 12th had a really good sense of humor. That was a great talk. Not all of these are recorded, but there's some really nice talks. They're really geared towards college level people, education in astronomy, so they can get a little technical, a little detailed, sometimes a little over your head. But there's some really interesting ones. Yeah, I saw the Mark Vogelsberger one as well.
Is any title that talks about magnetism and electricity, magnetohydrodynamics, just run. Just don't even go to that one.
Yeah. Yeah, it's going to be like way up here. Well, I'm glad a lot of people were able to enjoy those. And as long as you're enjoying them. Yeah, Jeff, I went to the same talks you did, April 12th and May 5th. I'll keep sending them out as they come out. And it really is a fortunate thing for us to be able to share this with the U of R, RIT, because I see a lot of the same people that we've had come do talks for us that are hosting these, and it really is fortunate for them to do that. So good. I'm glad you guys enjoyed it. Yes, Jackie, we all deal with work, and some of us get retired like me. You can do this stuff. Sometimes you could take some time off if you're working virtually. You could take an hour off and listen to it because they're only about an hour. Yes, I do email the link to them. when they were. Not all of these are recorded. I'll see what I can get as far as recording goes. Work is silly, says Mike Navin. All right, so virtual star parties. I have the list together along with the stuff we want. The stuff I want to look at with galaxies and start with star forming regions. I'm actually taking this right out of the May issue of Sky and Telescope. I'm adding a couple, 2 or 3 more objects to it. So if you had the May Sky and Telescope and you look at the star forming regions in there, those are the places that we'll visit with our C14 in hyperstar mode, and hopefully in hyperstar mode we'll be able to capture some of these things. Sometimes you need a little more magnification, but it's also harder to find them if you're not in hyperstar. So we'll see what we can get, and I'm looking forward to doing that. I'm going to try to start this on Saturday night. We'll see how far we get. We just need to have clear nights in order to do these things. So maybe Sunday. I don't know. It's a hit and miss over the next week or so with doing a star party. But stay tuned to your email. I'll let you know when it's done, and it should be interesting. Lots of cool stuff in the star forming regions in some of the galaxies. Most of these are nearby. Speaking of which, if you're interested in the star parties that we've done, and now as of this week, all of our last 13 monthly meetings are available on our YouTube page. If you do, just type in Rochester Astronomy section, Rochester Academy of Science, or ASRAS, you'll get to that site. You'll get to this page. The homepage has 2 playlists. One is the virtual star parties. Another is ASRAS monthly meetings. If I happen to like a video or something that I've seen online, it'll be a little further below there. But I encourage you, if you subscribe to this, you'll actually get notified when new things go up there. So after this meeting is done, I'll work with Dave Pesch to get that recording, and then I'll post it up on this site. And then when we do virtual star parties, I pull this all together in a recording, and then we premiere it together live. And then I'll take the recording of that premiere and then the actual recording of the star party itself and post it here, which is why you have 13 star parties instead of 7. One of them, we actually did the premiere and the talk through all in the same one. Otherwise, it'd be 14. So look for the YouTube page. All right, upcoming events. Tomorrow night, we'll have member observing, weather permitting, and it looks like we'll be able to have some. It looks like it's going to be about 20 to 30% coverage, cloud coverage, which that can be. It could be actually clear. You never know, but it could also be overcast. So I'm going to give it a shot tomorrow myself to go to the site and see what we can find. And I think there's a few other people thinking about going out there tomorrow night to do some observing. So. At dusk, look for me there, and we'll try to get some observing done in May at the site. Our board of directors meeting is virtual. It's on Wednesday, and if you want to go, shoot me an email. I'll be glad to send you the link for that meeting. If you have something you want to bring up, you want to see how we do business, you want to contribute to how we do business, glad to have you. I put out an agenda probably on Monday. I'm glad to include you on that agenda if you want something, if something you want to talk about with the board of directors. We have an open house the following week on Sunday. We would do it the 9th, but that is Mother's Day, and so we pushed it out a week. We know that Sundays are generally a pretty good day. Come out to the Ferris Center, and there it is. If you want to learn, the site, look at some of the buildings during the daylight so you get to know your way around, learn how to operate some of the telescopes, open and close the buildings there, come out on a Sunday. Typically that's a lawn mowing day too, so if you want to help with the grounds crew, glad to have your help there. And we'll be observing protocols for these in-person events that's coming up. Anything you want to add, Roger?
Not really. I had to turn my microphone on. Yeah, we're going to be hopefully mowing the lawn this Sunday, but by next Sunday we'll probably need it also.
Yeah, kind of imagine that's what we'll do. So, okay, thanks, Roger.
Okay.
So I've abbreviated our protocols. They were pretty wordy last time, but we still need people to sign in anytime you're at the site. The sign-in sheet is right when you walk in the door up the main ramp on the right-hand side on that table. There's a sign-in sheet. So we know who's there, and that we have to do contact tracing if somebody comes down with a case of the COVID virus. Anytime you're going to be less than 6 feet apart from anybody, you must wear face masks. And the occupancy of the Wolk Education Building is under 50% of capacity. The building capacity is 60 people, so no more than 30 people in there. And then the domes or the cave observatory or the Wolk rollout buildings, no more than 4 people in each of those. Both bathrooms will be available for use. Just please wash and sanitize your hands before and after you use the bathrooms. And if you're using wipes, just dispose of them in the trash can. Don't flush them, please. Pretty straightforward there. I think you guys have been through these before. All right, something new, and we have to give great, huge thanks to Tony Golombek. You have not seen astronomy section wear in ages. I don't think I've seen it as long as I've been a member, other than other people wearing it. No, I shouldn't say that. Joel did a run a few years ago. But as you can see on this screen, there are all kinds of gears. T-shirts, light and dark, big logos, small logos, RochesterAstronomy.org in the back. There's hoodies without a zipper, with a full zipper, and a big logo, small logo with a big zipper, a big logo on the back of a zippered one, and then 4 different kinds of fleece garments to wear. We actually looked into doing a hat, but that was going to be a little difficult to do with the embroidery that had to be done. So another time, perhaps we'll look at that. I shortened the URL because it was a long URL. I went to tiny URL and created this one, and I'll send this out again later as well. But Tony sent out an email this afternoon as well, and at each of these images that you get on the email has a link to look at the sizes and the colors. And so there's all these colors available. It's really pretty rich selection to draw from. And we have to give a big thanks to Tony. I challenged Tony to do this because he was talking about getting stuff. And I said, you want to lead it? And he led it. And he knocked it out of the park. So thank you, Tony, for pulling all this together for us. The key is when you go to this link, you'll get all these different things to order from, but you'll also have an order form on there. You need to get that back to Tony by 11:59 on June 5th so he could place the order, and we can all get our stuff soon and not be waiting till October, November, December for it. But the sooner we can get our order in, the sooner we can do this. And we'll do this more often. We'll try to do this more often in having astronomy section gear available to us. Tony, any other comments? He's got a comment. He's going to type. All right, I summed it up. Great. Again, thanks. Thank you, Tony Golombek, for the fantastic job in pulling all this together. It was a lot of work. There's a lot of emails coming back and forth with, do we want this? What do we want to say? What kind of garments do we want? And Tony did a really good job of getting a very rich selection of clothing. If you like T-shirts, great. If you like fleece, great. If you like hoodies, it's all there. Long sleeve, it's fantastic. Thanks, Tony. All right, coming up in June is one of our favorite meetings. This is David Bishop's annual Astronomy Year in Review, which we will do on Friday, June 4th. We are going to attempt to do this 2 ways, and we're working on the logistics on it right now. So we want to do a virtual meeting via Blue Button, as we've been doing, and we want to try having an in-person meeting at the Ferris Center, distanced, masked, and we'll talk about how we're going to make that happen, whether people will be vaccinated. We really can only accommodate, I think, 25 people seated distance in the main room, and really the basement isn't really set up right now for us to host people down there. So we may have to do reserved seating, but I wanted to at least flash this to you guys that we are going to try to do an in-person meeting at the Ferris Center, observing all the guidelines, and they are less restrictive than they've been. So looking forward to actually getting together again with everybody that can make it virtually and in person. So we're going to work on that and hope to make it happen for the Friday, June 4th meeting, for one of our favorite meetings of the year. All right, a big event happening right after our meeting on Friday the 4th. On Thursday, June 10th, at sunrise, the sun will be already almost totally eclipsed for this eclipse. It's got an annular solar eclipse well up north in Canada. And from here at sunrise, we'll have a thin crescent moon at sunrise at 5:31, and it will last until about 6:37 a.m. That's all you got. You got an hour and 6 minutes. That's all it will last. And then you can go on your day as you would any other Thursday, knowing that you saw the eclipse. And we will have projected viewing from these three places. Charlotte Pier in Ontario Beach Park, Martin Road Park in Henrietta, and Hamlin Beach Park up in Hamlin. The two of those are on the water, have great over the water views towards the northeast. It's going to be rising at 57 degrees northeast. I also made arrangements with the folks at the Parks Department in Henrietta to open up the park at 4 o'clock in the morning to set up. So you probably, if you're going to be observing or you want to participate, you want to come early to get set up, because you don't know what you're going to run into. Get your scope set up, get whatever you're going to do with the as far as safe observing. But we will have public safe projected viewing from these three locations. I think Carol's at Hamlin Beach. I'll be at Martin Road Park, and I know that at least Bob Birch will be at Charlotte Pier and Ontario Beach Park. We can certainly use more people who are anxious to do this, whether it's participating with a scope or a projection or a beta filter over your scope to watch it. Glad to have anybody else contact me if you're interested in helping out. But it's a big event. The sun rises at 57 degrees northeast on the 10th, so should be pretty interesting to see what that annular eclipse will look like. I've heard it called devil horns, kind of coming up from the horizon. Should be interesting. Any comments? A lot of people typing. Reclining devil. One side or the other. It's a public event, Jeff. This is a public event. It's pointing to the side. Oh, this way. Pointing to the side this way. I think you're right. Reclining devil. Gotcha. So yes, this is a public event, which is why we're doing projected viewing, because that way somebody can stand at a distance and see the projected sun on a sheet or something. Good question, Jeff. Thanks. Got a couple people typing. I'll wait for these comments to come up, and then we'll go to the next one. Yeah. Yep. Steve says that RMSC will be sending public to Hamlin and Henrietta. So yeah, both to Martin Road Park and then the Hamlin Beach Park is where the RMSC will support us. I keep this slide in there to remind you to say the dates. Rochester Star Fest is August 27th, 28th, 2021. at the Fair Center. We have a great speaker. Alex Filipenko will be our virtual speaker for that event. So looking forward to hosting Alex for that event. Say the date. All right, and now I will turn this over to Donald Brighty, a PhD in theoretical physics and a former professor at Syracuse University, and did a lot of other work in the business world in the meantime. So let me turn this over to Donald. All right, Don, it's all yours.
Okay, it's doing this thing again. I have to re-upload, but that'll
Okay.
probably take a minute or so.
All right, that's weird. I'll talk to Dave Pesh about that. It's kind of bizarre.
Okay. Huh. Something's not right.
There it
Oh,
is.
there it is.
All right,
Okay.
it's all you.
Okay, this talk is entitled Wormholes and Time Machines. And I'm going to start with a little bit, let's see, where is slide presentation mode here? Right there. Nope. What am I missing?
You're already in slide presentation mode. You just need to just arrow back and forth to where you want to be.
Okay, last time it filled the screen when we did the test on Tuesdays. It, at least on my display, it's a lot smaller today.
So if you go to the bottom of your screen, there's a little 4 arrows pointing out to the corners, and you can full screen it. That's for everybody if you want to see that.
That actually did this. It's behaving quite differently from Tuesday. It toggles between these two settings, that and that.
Wow, we're not seeing anything different. Okay, now you're zooming in.
I was trying to see if I could change the, nope.
All right, so Don, if you go to the 3 ellipses up on the top right, you can make full screen.
I just did. Something's not working right.
I think we're seeing what you want us to see, although it's a little zoomed in right now.
I have one other version of this that might work better. Sorry about this worked perfectly on Tuesday.
It did too.
Let me browse again. See if this one is any better. For some reason, talk about technical difficulties. I think I have to start from scratch. I can't get up to confirm. I apologize for the problems, but part of it is my computer died and I'm working on an iPad.
Oh dear.
So let me see if I can do this from scratch. Let's see.
Well, the next thing we could do, Donald, is if you want to email it to me, I can open it up and present it if that might help.
I don't remember this two-step process from Tuesday either, where after it uploads, it's just a PDF. Why does it have to convert?
It converted last time too.
It must have been really. It's now doing that disappearing act again.
There it is.
I'm not seeing anything. Is it uploading again or what?
It's on the screen. You're not seeing it in the presentation?
No.
It's showing. You're on your title screen.
That was the wrong thing. I hit the video button. Let me try this once more. Sorry. I'm going to do this from. Okay, I cannot scroll anymore. Oh, there it is. Okay, browse. Browse. 2. Can you force a confirm? I can't move my screen.
Let me see. Let me take your presenter. All right, it's there, Don. I'll tell you what. If you want to talk to it, I'll move the slides forward and backwards. They're there. Can you see them?
Let me grab my. I have another laptop that it's on that will not handle big blue button because it's so. But that way I'll be able to see the slides. Let me grab it
Because
quickly.
I have the slides here and I can move them for you. We actually got together on Tuesday night to make sure that everything was all dry run, and we had a little bit of similar issues where it didn't load right the first time. We got a couple of times there tonight, but we got it working fine at the second try. And now it seems to be there was an upgrade done on Big Blue Button like Tuesday or Wednesday, I think, and Wednesday or Thursday it was, and so it's really just the small differences. So what I'll do is I will.
Once we got past the initial hurdles, it worked fine on Tuesday.
That's fine. You just tell me when you want to go to the next slide, and I'll move through it for everybody.
Okay, if you could go to slide 2.
Okay.
And I have it on my outdated laptop. Okay, I thought of some motivation. I discussed a trip to Alpha Centauri. Alpha Centauri consists of 2 stars, A and B, roughly 1.1 and 9/10 solar masses. So very interesting. A G star and a K star. And then Proxima Centauri is an M, a red dwarf, about 1/10 of a solar mass. In addition to being our nearest stellar neighbors, part of the reason, next slide, please. Now you should just have an addition at the bottom.
Yes.
Okay, is a couple of confirmed exoplanets and one what I like to call an optimistic blip. Proxima Centauri B is an Earth-like planet, a little bigger than the Earth in mass. Proxima Centauri C is a super Earth, somewhere in the range of 6 to 8 Earth masses. And Alpha A component of Alpha Centauri, the 1.1 solar mass, has a planet B, which is a Neptune, but it's a test of the direct imaging method, kind of using a high-tech coronagraph called NIR at the ESO Observatory in the Atacama Desert of Chile. And right now it's no more than an optimistic blip, but if it's confirmed, it'll be a great leap forward in technology. So we have a couple confirmed planets listed here, one possibility. So the system has suddenly become much more interesting. Next slide, please. So at the time this chart was made, New Horizons was our fastest spacecraft. Already the launch vehicle made it the fastest spacecraft. It got a gravity assist around Jupiter, and it uses hydrazine just for maneuvering course correction. So the launch vehicle plus the Jupiter boost gave it its velocity. It's roughly, if I round that 7.7 to 10, it's roughly about 1/10,000th of the speed of light and would take 55,000 years to get there. Its record has been superseded recently by the Parker Solar Probe, but that's not going anywhere but the sun. Although it did go past Jupiter and pick up some radio, not Jupiter, Venus, and pick up some radio emissions on its last pass. Natural radio, not civilization, obviously. Breakthrough Starshot is one of Yuri Milner's initiatives. It's a fleet of hundreds of nanocraft illuminating a light sail by an array of gigawatt lasers and getting it up to 2/10 of the speed of light. It's supposed to come online in a couple decades or so, and it would take only 22 years to reach the Centauri system. Kind of intermediate, but a lot closer to Starshot than New Horizons. Nuclear thermal propulsion, not shown on this chart, where you use a nuclear reactor to heat, say, a hydrogen propellant, would take about 100 years to the Centauri system. So Breakthrough Starshot, once it's online, is the best shot about getting results back, because once it gets results, it sends them back on a laser via the speed of light in the lifetime of the researcher. But these are all much longer times than we would like. So there's two space-time shortcuts which I'm using to mean space-time geometry modification. One, I understand you've already had a talk on warp drives. And I want to say one thing about warp drives, and then I'll concentrate on wormholes. At the beginning of our universe, according to concordance cosmology, the current view, there was a period of less than 10 to the minus 30th seconds of exponential expansion called cosmic inflation that was hypothesized to get around problems with Big Bang cosmology. The horizon problem, why is the microwave background so uniform? The flatness problem, why are the spatial cross sections so flat on large scales? And the magnetic monopole problem, where are they? We never see any. And they should have been formed at the high energies in the early universe. So those three problems were explained by positing this very brief 10 to the minus 32 or less seconds of exponential expansion, which was then followed by the ordinary Hubble expansion for 13.8 billion years. This exponential expansion was global across the universe. What a warp drive does is it does the same thing locally. So aft of the ship, there's an expansion of space-time. Forward of the ship, there's a contraction, the inverse to the cosmic expansion, but both happen locally rather than affecting the whole universe. So you sit in your warp bubble at rest, space behind you expands rapidly, so you get further and further from your destination while sitting at rest. Space in front of you contracts, so you get further from your embarkation point. Space in front of you contracts, you get closer and closer to your destination. It's a neat trick if you can pull it off. And it requires something called exotic matter that we'll get to a little later. On the left is a wormhole depicted as connecting two universes, but it could also be between two distant portions of the same universe. And the rest of this talk will just be wormholes. So if we could go to the next slide, which is just a title, so the one after that. Wormhole Revolution started with Carl Sagan writing Contact. He wanted to use as a plot device an alien artifact, an abandoned interstellar transportation system. And he asked the relativist, Kip Thorne, if it violated anything in physics. And Kip did what any good physicist would do. He asked his graduate student, Michael Morris, to look into it. And together they wrote a paper whose title and page from the paper, or part of it, is depicted below, in 1987, which started the Wormhole Revolution. Of course, they didn't think of this in any practical term. The subtitle is A Tool for Teaching General Relativity. They thought of it as a great motivational device. Next slide, please. So I have to say at least a little bit about general relativity. So G mu nu is a so-called second-rank tensor. It's a geometric object that each of the indices mu and nu independently go from 0 to 3. So they have 4 values, 0, 1, 2, 3. 0 is time, 1, 2, 3 is space. So 4 by 4 should be 16. But because of symmetries, it reduces to 10 independent ones. Same thing for the right-hand side, T mu nu. So this is actually a set of 10 independent equations expressed in compact form. And then G is Newton's constant of universal gravitation, C the speed of light. So that's just all constants. So what this does is relate geometry to the sources. Just like in electromagnetism, charges and currents produce the electromagnetic field. In gravity, masses and energy, mass energy, and currents of mass energy produce the space-time curvature, the geometry. So in John Wheeler's famous dictum, mass energy tells space-time how to curve, space-time curvature tells mass how to move, and that's general relativity in a nutshell. Now, there's 2 ways of approaching this equation. The canonical way is you specify the right-hand side, the sources. You have some given configuration of mass and energy and currents of mass energy, which is why T mu nu is called the energy momentum tensor, because momentum is just basically a current of mass or energy. And on the right-hand side, you have the Einstein tensor, which spells out the space-time curvature. So the general way, as in electromagnetism, is specify the sources, solve for the resulting field, which for relativity is the geometry, the curvature. But they turned this on its head and said, we know what we want. We want a wormhole that's traversable. So we'll specify the geometry and see if we can get any physically realistic sources on the right that could create that geometry. So they solved Einstein's equations backwards from the usual approach. Next slide, please. And that's just summarized in the final box. Specify the geometry, solve for sources. Now, since I'm going to show you what one descriptor of the wormhole looks like, I thought I would take probably the easiest thing to explain in general relativity, the space-time metric. And for those of you who aren't familiar with it, try and make it understandable. So we should now be on the slide that says Einstein's general relativity dash metric.
Yes.
So in flat space in Cartesian coordinates, the total distance dl between 2 points A and B, by if they're separated dx in the x dimension and dy in the y coordinate, it by the Pythagorean theorem, dl squared is dx squared plus dy squared. If we added a third dimension out of the page, length, width, and now height, we would just add a dz squared. And if we wanted 4 dimensions, say w, we would just add a dw squared and continue doing that for as many spatial dimensions as we want. But what we really want is space-time. And because of the invariance of the speed of light from special relativity in all frames of reference, which lead to the so-called Lorentz transformation, Next page, please. You notice that dt squared enters with a minus sign. So we have three positive squares of spatial distances and a negative one of time. Now it doesn't matter. You could flip these and make the time positive and the space negative. As long as you pick one of the two conventions and stick with it, you'll get the same results. I just happened to pick the one where space was positive. So in space-time, we have that sign difference, and we're still in flat space-time. Now, this could look different if we go to a different coordinate system. Next slide, please. So if we go to spherical coordinates in three-dimensional space, we have a radial coordinate r, dr squared, and then we have two angles, theta, which is the polar angle from the z-axis, and phi, which is the azimuthal angle from the x-axis. And they enter in this way, in r squared times d theta squared plus sine squared theta d phi squared. And for those of you more familiar with latitude and longitude, if we interchange sine theta and cosine theta, theta and phi just become lat and log. Okay, sticking with the original theta and phi, if we add in time, we again do it with the opposite sign. So either one of those, let's say 4DST, four-dimensional space-time, is actually the same space-time in two different coordinate systems, Cartesian TXYZ or spherical TR theta and phi. And the only reason I went through all of this is A, it's fairly easy to understand, unlike most of the more esoteric things like the curvature tensor and relativity. And B, I'm going to show you what the actual wormhole space-time metric looks like. So here is, next slide, here is the space-time metric for the Morris-Thorne wormhole. If you go back a slide for a moment, you see that same r squared d theta squared plus sine squared theta d phi squared. Okay, forward again to the Morris-Thorne is in the Morris-Thorne. So it is spherically symmetric. But the r and t terms now have some functionality. And they involve two functions. The phi of r is called the redshift function, and the b of r, which determines the wormhole shape, is called the shape function. So what Morris and Thorne did was they adopted an engineering approach. They wrote a list of specifications for the wormhole. Like, for instance, gravitational g-forces like tidal forces should be small. You don't want to be A, uncomfortable, and B, suffer physical harm if they're really big. So we keep the g-forces as small as possible. Second, you want the travel time to be reasonable. You could pick anything you want, a second, like a Stargate you just walk through and you're there. But that constrains the wormhole severely. Or you could say a minute, a day, a week, a month. If you want to keep the wormhole reasonable in terms of what's required to produce it, you might say several months or a year. If you were going, say, 100,000 or 1,000,000 light years, you may be willing to travel for a year to get that kind of, or if not 6 months, 3 months, whatever. You pick the specifications and the equations tell you what you need in order to produce that wormhole. So you solve for the type of matter required to produce this geometry. And next slide, and I'm now going to show you what the Morris and Thorne engineering specifications for the wormhole. The first four he called basic wormhole criteria. It should look and behave like a wormhole. He wanted a simple mathematical form, so it's spherically symmetric and static. Physicists love symmetry. It makes the equation simple and easy to solve. And if I may tell one joke, a dairy farmer was having trouble with milk production and hired a physicist. And the physicist was scribbling equations on a whiteboard. And after about 6 months, the dairy farmer asked the physicist to give an account of what he had done for his herd. So the physicist walks up to the whiteboard, draws a circle, and says, "Assume a spherical cow." But that's a typical physicist approach. Keep things as simple as possible and try and just capture the essentials. Okay, so we're going to have it spherically symmetric and static. We want it to obey Einstein's equations. We want it to look like a wormhole, so they defined it as connecting to AF stands for asymptotically flat regions, which means the further away you get from the sources of curvature, the flatter the universe becomes. And you want no horizon. Remember, a horizon is a one-way membrane, like around, say, the simplest Schwarzschild black hole. You can enter but not exit. And you want two-way travel, so no horizons. So those are their first four criteria. Next slide, please. Then they had what they called usability criteria, which I've already mentioned. Things like physiological comfort, convenience, and actually safety when it comes to G-force. So gravitational force is bearably small and reasonable travel time. Pick whatever number you're willing to live with, recognizing that if you pick a second, it's going to be a severely restricted wormhole that's going to take a lot more exotic matter, for instance. And next slide. And finally, they added three more, one of which we can't really say much about. He called number 7 aesthetic. And it's simply that the stress energy tensor, the source on the right-hand side of Einstein's equation, be something physically reasonable, some kind of matter and energy that makes sense to us, that doesn't seem to defy anything in physics. Unfortunately, for most wormholes, this is violated because of the thing I'll be getting to, exotic matter, which has a negative energy density. So instead of gravitational attraction, it's gravitational repulsion to hold the wormhole throat open so it doesn't collapse. And then you can travel through the wormhole. Number 8 is perturbatively stable. You don't want the wormhole to become unstable by traveling through it. If you travel through it and that destabilizes it and it collapses and crushes you, that's no use. If it's so unstable that a stray particle of dust going through or a stray photon going through, these are the extreme cases, destabilizes it. So you want it to be stable not only against a photon or a particle of dust, but an entire spaceship going through, and that's what's meant by perturbatively stable. And finally, number 9, which is kind of pie in the sky, possible to assemble. Obviously, this would require extremely futuristic engineering that we can't even begin to imagine. Okay, next slide. Okay, so here's some issues. It requires something for the most part called exotic matter, which has negative energy density. Does such a thing exist? It does in quantum field theory. Is it available? Well, that's a big catch. The original wormholes required a galaxy-sized mass, galaxy of exotic matter. Obviously, very impractical. They got it down to a Jupiter-sized mass. Still a lot, but a lot better than a galaxy-sized mass. And then someone named Matt Visser, who literally wrote the book on wormholes. I'll show you his book at the end, called Lorentzian Wormholes, came up with solutions that required arbitrarily small amounts of exotic matter and kept it away from the ship and crew. Because my second thing in the line above, if we don't know that much about it, how would it affect people, or how would it affect the integrity of the ship? So we'll be careful. And just like in the warp drive, where it's in a warp bubble containing the ship but not touching the ship itself, it's in the outer portions of the throat stabilizing it. Okay, wormholes I would show may be convertible into time machines and cause causality violations and chronology violations. So that obviously could cause a problem since people think such things should be impossible. I'll get to the various responses to that a little later. Topology change. A lot of theories in physics have topology change constraints. And when you create a wormhole, you're doing what a topologist would describe as putting a handle, like the handle on a coffee cup, on space-time, an alternate path to get from here to there. Once the handle is on the coffee cup, you could go from between the 2 points of attachment remaining on the cylindrical portion of the cup, or you could go around the handle. So you've added an alternate way from here to there, changing the connectivity. And there's a lot of reason to think that maybe such changes in topology are forbidden. Okay, so a wormhole has several things possibly going against it. Now, how might we find or construct one? So mostly by very advanced futuristic methods. We could use the method in Carl Sagan's Contact, find an alien relic wormhole that high-tech civilization far in advance of us took care of for us. We just have to discover it and use it. A second one is to find, enlarge, and stabilize a primordial white wormhole. What do I mean by primordial? In analogy, people talk about primordial black holes. There are two kinds of black holes. Black holes that come into existence, say through collapse of a massive star. So they weren't there at the beginning of the universe. And then what people in some papers call eternal black holes or primordial black holes. They're part of the initial conditions of the universe and were there from the start. Well, similarly, there might be primordial wormholes there from the beginning of the universe. They didn't have to form or be constructed. So if we could find one, enlarge it to traversable size and stabilize it, because chances are they would be quite small, just like primordial black holes. The third one requires some even further out thinking. If you apply quantum thinking to gravity, space-time at the smallest levels should be in continual flux, and that is referred to as quantum foam. If we compare it to an aviator flying over the ocean, at a great height, he sees a glassy, smooth surface. He comes down a little and sees larger waves, a little lower, smaller waves, a little lower. He even sees the foam on the waves. Space-time, by analogy, if we apply quantum principles, is like that. It's smooth classically, but as we look at tinier and tinier distances and approach the so-called Planck length of 10 to the minus 33 centimeters, far smaller than an atom or a nucleus or a proton and neutron, etc. We approach this incredibly tiny distance. That's where quantum gravitational effects are expected to be extremely active, and space-time then would look like foam. And since it's foam, it's undergoing all kinds of change, things popping into and going out of existence. And in this foam, topology change is allowed. So a wormhole could pop into existence and then go away. And if you could find one of these transient wormholes in the quantum foam, enlarge and stabilize it. You could also irradiate a black hole with negative energy, as long as we can get a beam of negative energy to begin with. You can entangle and then separate two black holes or attach them by a cosmic string, which is another kind of singularity. It's a line singularity. For those of you familiar with solid state physics, it's comparable to a line defect in a crystal. But anyway, it can be thought of as a line-shaped singularity of infinite density, classically, and zero radius, but it now has extent. So it's like an infinitely thin cylinder. That's a cosmic string, packing a divergent amount of mass into it. So these are all obviously far, far outside our reach. Next slide. I'm now going to address the issue of exotic matter. In quantum physics, there's something called virtual pair production and annihilation. There's also real pair production and annihilation. If you have a gamma ray, say in the field of a nucleus, for instance, it can suddenly go out of existence and be repaired by be replaced by an electron-positron pair, where a positron is the antiparticle to the electron, same rest mass. So as long as the gamma ray has energy at least equal to twice the rest mass of an electron, one for the electron, one for the positron, it can create a particle-antiparticle pair, electron-positron. And then if they encounter each other, they annihilate, and we're back to gamma rays. In the quantum vacuum, we get virtual rather than real particle-antiparticle pairs. So there's something called the time energy uncertainty principle, delta E, delta T greater than or equal to h bar over 2. H bar is the so-called reduced Planck's constant. Planck's constant divided by 2 pi. And that's one of the many uncertainty principles. So you can think of this as you borrow energy from the vacuum for a time delta T. This tells you how much energy delta E you can borrow. And then when the two particles annihilate each other, they pay back the debt, to put it in banking terms. So next slide, please. So it turns out there are real effects of virtual particles. There's something called the Lamb shift of the hydrogen spectrum. There's two energy levels that classically should be identical, and therefore there should be no transition between them because there's no energy difference to emit or absorb radiation. But these two levels are different due to the effect of virtual particles, and can only be explained in that way, and can be explained exactly in that way. It's one of the triumphs of what's called quantum electrodynamics, which is the quantum theory of electromagnetism, among other things. And there's something called the Casimir force. If you have two charged conducting plates, one with positive charge, one with negative, they attract each other electrostatically because unlike charges attract. If you have two neutral plates in a vacuum, yes, there should be a slight attraction due to Newton's law of universal gravitation. But other than that, if it's a true vacuum and it's been isolated from, no thermal effects, no air currents to conduct heat, there's no vibrational effects. It's totally isolated, say floating out in space in a perfect vacuum somewhere. There should be no force other than Newton's universal gravitational attraction. But it turns out there's an additional force which is due to the quantum vacuum. And the way to think about it is the conductors impose boundary conditions on the electromagnetic field. The field has to be zero at the conductor, a node. It's like you have a violin, cello, or guitar string, and at the points of attachment, it can't have any displacement, it can't move. So you have to have a node of the waveform at the two attachment points of the string. So when you apply this kind of boundary conditions, it imposes a kind of quantization where only certain frequencies or wavelengths fit. So outside the plates on the left and the right, all possible frequencies or wavelengths fit. Inside between the plates, only, for instance, in the reddish orange, a half wavelength fits. In the green, you have a complete cycle, a full wavelength. In the blue, you have 1.5 or 3/2 of a cycle. And in the purple, you have 2 complete cycles or 4/2. So half a wavelength, 2/2, 3/2, 4/2, only an integral number of half wavelengths fit. The same thing happens for a violin, cello, guitar string. An integral number of half wavelengths of the vibrations of the string fit. So because there's a different content to these virtual vibrations. Now, what I want to say about this virtual field, there's a particle picture and a wave picture. The particle picture is a virtual particle-antiparticle pairs creating and almost immediately being destroyed. But that's equivalent to having a field. The field picture is this tiny, tiny virtual electromagnetic field, and all frequencies and wavelengths outside the plates, between them, only a discrete set. There's still an infinite number, but that infinity is fewer in some sense than what exists to the left and right. Now, if you have an electromagnetic field, it has an associated energy. So there's an energy between the plates due to adding up all the modes that fit. That's different from the energy outside the plates, and that's the origin of the Casimir force. And it's also the origin of, you can think of it as a Casimir energy or a Casimir field in complementary views of looking at it. Next slide, please. So for proof of concept of exotic energy, we have the Casimir energy, which has been measured in the lab. Extremely delicate measurements involving either an atomic force microscope, AFM, or a MEMS device, micro electromechanical devices, which vary in size from less than a micrometer to several millimeters. And these devices exist currently. Their use is well understood, and they can be used to measure the Casimir device and the Casimir effect. And at the scale at which these devices work, they have to be taken into account as part of the operation. The Casimir force affects these micro electromechanical devices. The inflaton field is the field that drove the cosmic inflation I talked about at the beginning in the analogy with the warp drive. And it has negative energy density. The dark energy in modern concordance cosmology that's apparently driving an acceleration of the expansion. Also, most of its explanations involve negative energy. So two of these proofs, cosmic inflation and dark energy, are hypothetical, but they seem in many ways to be the best fit to our current understanding of cosmology. One of these, Casimir energy, has been measured many times in many different labs and always replicated. Okay, next slide. Time machines, it's just the title slide. So going to the next page. Traveling into the future is easy. If we don't do anything but just sit here, we travel at what you might call a rate of 1 second per second into the future. But there's 2 ways of increasing that. Special relativistic time dilation, like the twin paradox. We go away from the Earth at a very large fraction of the speed of light, a high V over C ratio. V is velocity of our ship. We return and find out a lot more time has elapsed on Earth. Everyone we knew is long since dead and gone. because of special relativistic time dilation. It really slowed down for us. General relativistic time dilation, we go in a large gravitational field, like maybe orbit a black hole, our clocks slow down. And this is a real effect. And if we didn't correct for a GPS, which people use every day, would not work. And I like this example because people think of general relativity as pie in the sky, very esoteric. But without a general relativistic correction, GPS wouldn't work. The clocks in orbit are in a slightly lower gravitational field than the clocks at the ground. So the clocks on the ground in ground-based GPS devices run slower than the clocks in the GPS satellites. And if you don't take that into account, this general relativistic effect, you get an error called GPS drift. And GPS drift makes it look like you're moving when your car is sitting stationary in your driveway. So you sit in your driveway long enough and you find yourself in, say, Biloxi or Chattanooga or something like that, according to your GPS system, when in reality you're still in your driveway, which would make GPS fairly useless. But by taking the general relativistic time dilation into account and correcting for this difference in clock rates, tiny as it is, GPS is workable and usable. So a triumph of general relativity in everyday life. Next slide. Okay, travel into the past is much more problematic. So if you take a wormhole and take the throat you're going to not the throat, the mouth you're going to exit from, say on the right-hand side, just to pick a direction of the wormhole in the depiction, and you apply one of the above two methods, either move it at a very high fraction of the speed of light and then return it to its original position, that will cause time to have slowed down at that wormhole mouth. If you put it near a black hole, like say you arrange the mouth so it's in orbit in a ship around a black hole, or it could be a neutron star, which would have a lesser effect than a black hole, or a white dwarf, which would have an even lesser, but some source of high gravitational field, time would slow down at that mouth that's in orbit. And then you return it to its original position because you probably aren't interested in being in an orbit around a black hole. And in either of these two scenarios, you then go through the wormhole. When you emerge out of a mouth where time has flowed a lot slower than the mouth at which you entered, and you've converted it to a time machine. So that's one way of getting a time machine. Another one, way back in maybe the 30s, Van Stockham came up with a solution to the field equations of general relativity involving an infinite rotating cylinder of dust. And it produced what are called closed time-like curves, which I will explain a few slides hence. And it creates general relativistic frame dragging effects. To put it in Newtonian terms, the inertial frames are dragged along by the rotation, and that causes the light cones to tip. And eventually they tip so much, instead of pointing to the future, they point to the past. So your future now becomes your past, and you can travel to the past without ever leaving your light cone. Tipler came up with a variant of this for a finite cylinder, but unfortunately it required matter even denser than nucleonic matter. If it were made of solid neutronium, it may not be dense enough to get enough of an effect. And this matter, how you would get it, extremely advanced engineering. True, it might be worth it to get a finite cylinder. And second, it would have to rotate so fast that no known physical material, including solid neutronium, could withstand it, and it would be broken apart. So that's kind of a self-defeating time machine, so far at least. An infinitely long pair of cosmic strings crossing each other, and variants of warp drive methods. So there are four or five ways of getting a time machine. Okay, next slide, please. So I apologize for those of you who are quite familiar with these concepts, but since I don't want to assume anything, I want to at least say something about space-time diagrams and light cones. First of all, relativists almost invariably set the speed of light to one light second per second. In a sense, that means you're measuring space and time in the same units. A second of space and a second of time is the time, I'm sorry, a second of time and a second of space is the amount of distance light goes in a second, or a light second. And because you have now one light second over 1 second, 1 over 1 is 1, the arctangent of that is 45 degrees, or 45 degrees has a tangent of 1 is probably a simpler way of putting it. So lines on a typical space-time diagram at a 45-degree angle represent light speed. So in this diagram with only one space dimension, space is to the right, say the x coordinate, time is up. If you're sitting still, you go parallel to the time axis at 0 velocity. If you're going between 0 and the speed of light, you go somewhere between 0 and 45 with the time axis. At the speed of light, you're going 45 with respect to the time axis, and greater than the speed of light, or superluminal, you're going at a greater than 45-degree angle with the time axis. So bearing that in mind, on the right is the light cone. The boundaries of the light cone are the paths of light rays going at v equals c, so they're at 45-degree angle. Velocities between 0 up to but not including c are within the light cone. Velocities greater than c are outside the light cone, greater than 45 degrees. So at an instant of time, you're at that vertex of the light cone. You are here. And your future light cone above you contains all possible trajectories you could execute going less than or on the boundary equal to the speed of light. So that means the future light cone also contains all causal signals, any signal you can send at less than or speed of the light. So it contains both anything you can physically reach by traveling between 0 and c, and anything you can influence by sending a signal between 0 and c. The past light cone is the inverse of that. It contains everything that could either reach you or influence you with velocities less than or equal to c. So that's a light cone. If anyone has any questions, let me know. But I think most of us more than likely are familiar with these concepts to some extent. Okay, next slide. So here's where CTCs, close time-like curves, come in. Here's a space-time diagram. On the left, the cones stacked above each other. If you just sat still at rest, your light cones would stack up nicely. But notice they always point to the future. Even if that line were at an angle, so you were going at some velocity, at every point, the light cone would have its vertex on the line, but would still point straight up to the future, the way we normally think of it. But if you have a high enough curvature of space and time, due, for instance, to extremely high angular momentum density from one of those rotating cylinders, or due to converting a wormhole into a time machine, just to mention two examples, the light cones tip over more and more. So you start to go up into the future, and then your light cone tips a little, and then it's straight across, and then it's pointing downwards, and then it's straight down, pointing to what we would normally call the past, but it's your future light cone that does this. So by going into your future, you arrive at the past. And these things form typically closed loops, so they're called CTCs, or closed time-like curves. And the way you use them for travel is you join one of these closed time-like curves at some point in the future. Say you go from A to B and join the CTC. You travel around it into the past, leave at C in the past, and now you're at some point D away from it. If I had drawn this to scale, D would be a lot further away, where space-time is a lot more normal now, and you'd still be in your past. So neat trick, while remaining in your future light cone, you end up in your past. Next slide. So 3 simple steps to convert a wormhole to a time machine. I'm sorry, but I have to say this reminds me of a Steve Martin routine way back when. He had 3, he might have called it 3 easy ways to become a millionaire. And step 1 was acquire $1 million. And this is kind of like that in terms of what we can do today. Step 1 is acquire a traversable wormhole. Step 2 is induce a time shift, either by special relativistic time dilation, a twin paradox kind of thing. Go away at a very high velocity and then come back, or go near a black hole for a while and come back. Either way, time is slowed down at the right hand mount by either special or general relativistic time dilation, and you've apparently created a time machine. Now, can one really do this? Next slide. Okay, here's 2 more time machines. The left-hand one is the rotating cylinder. It could either be Gott's infinite or Tipler's finite cylinder. And you enter the time machine at a point where the light cones are starting to tilt, and then you get into the severe tilt. And simply by going around either the infinite cylinder in the one case, or the finite but almost impossible to construct one in the finite cylinder case, simply by going around the cylinder in the direction of rotation, you go further and further back into the past. The second one I couldn't resist putting in because of the connection with Doctor Who. A couple of physicists wrote a paper in which they tried to capture the essence of the TARDIS, which is in Doctor Who terminology, time and relative dimension in space, referring to Doctor Who's means of transportation. And they came up with a space-time metric shown below. It has one feature we haven't seen, in that there's a cross term, dx dt. A lot of metrics don't simply have the squares, but they also have the cross terms. They're general quadratic forms. They wrote 2 papers. A highly technical one called traversable achronal, meaning it violates chronology; retrograde, meaning it's going backwards in time; domains in space-time, whose initials again spell TARDIS. And they gave their real affiliations. Then they wrote a simplified form called the Blue Box White Paper, and in it, one of them claimed to be from Gallifrey Polytechnic Institute, GPI, and the other one from Galtech with a G instead of a C, in analogy with Caltech. And of course, Gallifrey is the home planet of the Time Lords. So it was a cute little thing. But it was all solid physics. And you can see they were using a close time-like curve. In fact, they constructed an annular region between the 2 circles, where every concentric circle was a close time-like curve within that annular region, and posited that as the mechanism of time travel for the TARDIS. Next slide. So now some of the fun stuff, time travel paradoxes. Next slide. when I was an undergraduate, I got tired of discussing the grandfather paradox, which, as everyone knows, you go back in time and either shoot your grandfather before he met your grandmother, or in the more benign version, since you know the day when he first meets your grandmother, you interfere with him meeting, either physically restrain him or knowing he really loves science fiction, say, I'm from the future, let me tell you about time travel, and he becomes engrossed and doesn't do whatever it was that caused him to meet your grandmother. And of course, you could do this with any progenitor, but people would always say, well, yeah, you could, but would you really? And you have a choice, but just the fact that you could means there's paradox there. Potential. So I came up, people were when I was an undergraduate, there was a lot of talk about tachyons, which went faster than light and backwards in time. So I'm sure this isn't original with me, but as an undergraduate, I didn't know much about, I didn't even know people research these things, so I didn't look for paper, but I thought it should be easy to construct a hard version of the paradox, and I came up with this, which probably many people have. So an ordinary electromagnetic wave leaves its dish, goes forwards in time, and is picked up and detected. And the detection produces a 0-1 enable signal. And since it's detected, it's a 1, the tachyon transmitter is enabled, it goes backwards in time to the receiver. It's detected, producing a 0-1 enable signal. Now, if you didn't have the NOT gate, it'd all be perfectly consistent. You detected in the future, say, enable transmission to the past. Detected in the past, say, enable transmission to the future. No paradox. But by inserting that NOT gate, if you detected the tachyon in the past, the 1 gets converted to a 0. You don't enable the transmission, so it's not detected in the future. So the tachyon transmitter was not enabled in the future, which means you didn't detect it in the past, which means the electromagnetic transmitter was enabled. So in hardware, we've duplicated the grandfather paradox, and no one can bring human motivations and what people might or might not do into this picture. Next slide. I'm going to show you 3 more time travel paradoxes. Here's one where people might argue human motivations. A ship goes through a wormhole. I just picked Star Trek ship. Like the Enterprise. It goes through and arrives far enough back in time, or it could use its warp drive, obviously. It could get to the point where it's about to enter at the same time it entered, and it fires and destroys itself. And if you want to think a more realistic ship, maybe phasers don't exist, use lasers, use kinetic mass driver, use space torpedoes that explode when they hit the ship, whatever. But somehow you destroy your ship and prevent it from entering, but you didn't go through, so you didn't prevent it from entering. But because of the human motivation factor, someone came up with, next slide, self-intersecting billiard ball trajectories. This is really cute. A billiard ball goes on a trajectory such that it goes through the wormhole, comes out in the past, and is made to curve around in such a fashion that it gets back just as it's about to enter, and it deflects itself from entering. But if it didn't enter, it didn't go around, so it didn't deflect itself, so it did enter, and so on. And these self-consistent, well, I don't know if consistent is a good word, but these trajectories have been shown to actually exist. So no decision whether to fire on your ship or not in this one to save you. Okay, next slide. And this is an example of a bootstrap conjecture. You do decades of research, discover time travel, create a time machine depicted as the TARDIS, but in the process, you've ruined your health, your wife's divorced you, your kids don't talk to you, you never got to spend any time with them, you've never taken a single day of vacation or moment of relaxation. You want to save yourself the problem of doing this. So you go back in time and hand yourself the completed research. But the question is, if you didn't do the research in the first place, where did it come from? So it's also called the author paradox. You could use it with somebody writing their one great novel also. There's a DNA version of this where you supply one or more of your progenitors. You go back in time and not when you're an old man, and become one of your progenitors. Or there was a 2014 movie, I can't remember the name, where someone went back in time and became their own father. They went back in time a second time with a high-tech sex change operation that allows conception to take place, and became their own mother. So Jack, Jill, and their baby were all the same single individual. But in that case, where did their DNA come from? Another bootstrap paradox. How am I doing on time, by the way? Okay, well, at any rate, next slide, responses to time travel. Matt Visser, the one who I said wrote the book on wormholes, listed 4. The radical rewrite conjecture, majorly revised physics, alternate universes, alternate histories, alternate timelines. So this would fit in well with, for instance, the Everett Wheeler interpretation of quantum mechanics, the so-called many worlds interpretation, and it fits in with a lot of multiverse theories. The Novikov consistency conjecture. You can't change history. You could go back, but the universe will prevent you from changing history. Unfortunately, there's no good mechanism to enable that. Hawking's chronology protection conjecture. Closed time-like curves are not allowed, but traversable wormholes are okay. Something intervenes in preventing a closed time-like curve, like back reaction from diverging stress energy, and the boring physics conjecture. Anything like a wormhole that could even in principle produce a time machine can't exist. Okay, next slide. I think I may be running a little long. I haven't been paying much attention.
Yeah, you're a little long, but if you could wrap it up in the next 5 or 10 minutes.
Okay, sorry. I lost track of, well, I think that fooling around with trying to get it to work probably took 5 or 10, but I probably talked more than that. Okay, to make this long story short, there's Einstein's equation at the bottom with a second source term, a quantum term, and that quantum term can diverge and prevent time machine formation and even disrupt the wormhole. So if vacuum energy fluctuations go through the wormhole and then arrive back at the same time they entered, 2 copies go through, they both go around and come back at the same time, 4 copies. This obviously will diverge, and this extremely divergent source term will far outweigh the classical term setting up the wormhole in the first place, destroying the wormhole geometry. Unfortunately, it's not generic. The next slide, I was going to explain the Roman ring, chain of 2 or more wormholes. And I'll just tell you the gist of it. Neither one is a time machine, but the total is the conjunction of the 2. So you enter a wormhole at A and leave at A prime outside your past light cone. Even though it looks like you're in your past, it's ambiguous. A and A prime, because they're not related causally by having A prime in your past light cone. There are some frames of reference or observers who will see A prime not in your past but simultaneous, and other frames of reference where A prime will be in your future. So you're not in your unambiguous past. So by doing this, you haven't violated anything. You then travel from A prime to B, the second wormhole entrance, and emerge in B prime. B prime is not in B's red past light cone. So there's no time travel paradox there. But B prime is in A's black past-like cone. So by going through two successive wormholes, neither one of which caused a violation, the sum total of the two caused a violation. And the feedback mechanism is not operative to protect you. Okay, couple cute things and I'm done. Three time traveler events. In Perth, Australia, May 05, that's a plaque in the town square. They held a time travel party, invited time travelers. No, as far as we know, no one showed up. I'm sorry, that was March. In May of the same year, MIT, not to be outdone, held a time travelers convention, placed invitations on acid-free paper and obscure library books that they thought would be likely to be preserved and exist far into the future. And on the RSVP form that was included with the invitation, one box you could check was I'm from the future and would like to attend. But the biggest one in my estimation was Stephen Hawking. He sent out an invitation in 2009 for a party he held in 2013. So the party was 4 years before the invitation was sent out. There's a copy of the announcement. He gave the location, including the Latin lung, the universal coordinated time, 12 o'clock, noon, the date, etc. He hoped that these things, because of their novelty value, would be preserved a long time into the future, and someone would find it when time travel had possibly been invented and come back and attend this party. No one did. Next slide. Very quickly, two physicists did a search of the internet for evidence of time travel. Two had to do with prescient content, talking about astronomy, things that weren't known at the time of the discussion, submitting an inquiry to an astronomy search engine about something that was not yet known, and then searches for requests for communication predating the inquiry. And a massive search of the internet and social media was conducted. None of this was found, obviously. What it proves is anyone's guess. And here are the books. The top two are highly technical, and although there's a few readable things here and there, the left one is Matt Visser's classic. They both require quantum field theory and general relativity, very good knowledge. The bottom three are popular. The third one by Kip Thorne, who originated the Wormhole Revolution in response to Carl Sagan, also was the science advisor for Interstellar. And in the process, he talks about wormholes and black holes and things like that. And sorry I ran over. That's my talk.
No problem. Thank you very much, Donald. Questions for Donald? There's a question in the chat from Nick that says, what stops the time dilation from propagating through the space-time geometry of the wormhole?
I don't know what is meant by that. The time property occurs because one mouth of the wormhole, time has traveled more slowly. What do you mean, the effects rather than that in and of itself? I mean, obviously effects can propagate through. That's what happens with the possible mechanism for preventing time machines. You have virtual electromagnetic field go through, it arrives backwards in time, and if it can come around at the same time, it doubles what went through, come around again, it quadruples, and keeps doubling indefinitely, causing a divergence, which means the wormhole is disrupted. So in that sense, yes.
Dick's typing. Maybe you can clarify it in a minute. Jeff says, how might a primordial wormhole be detected?
I think part of that would be having technology that currently doesn't exist. We might find a macroscopic wormhole, but it may have effects in the surrounding patch of space that it's in. But how you would detect a primordial one, or even a transient one, which would be even worse, is anyone's guess at this time.
Any other questions for Donald? Somebody typing. So what is a tesseract? We saw that at the end of Interstellar. What kind of a construction is that?
It's simply a four-dimensional cube, also called a hypercube, similar to a hypersphere, which is a four-dimensional sphere. If you just took, say, to make it slightly mathematical, the equation for a cube, for a sphere, say, and wrote it in one additional dimension, you would get a hypersphere. So to put this in perspective, if we start with a line, which is a one-dimensional object, in a sense, or a line segment, in a sense, a square or a rectangle is a hyperline. It's like forming a two-dimensional version of the line. And a cube is like a hyper square, which in turn is like a hyperline. So a cube is forming a three-dimensional version of the two-dimensional line. Now, it's hard to visualize things in greater than 3 dimensions, but if you do the same thing, you got to go from the line to the square and then from the square to the cube and repeated that iteration one more time, you would end up with a hypercube, also known as a tesseract. So it's basically a four-dimensional cube instead of a three-dimensional cube. So, okay, think of it this way. When you have a square, the faces of the square, which are the lines, are simply lines. When you have a cube, the faces of the cube are squares. Iterate one more time. When you have a hypercube, the faces of that object are cubes. So each time you go up one dimension, the things that constitute each face also go up one dimension. But try and picture something whose faces are cubes, and it's a little bit hard. There are some interesting depictions you can locate online of broken down tesseracts or hypercubes, where they explode them apart and show you here's the individual cubes and here's lines indicating how they connect to each other. But what they can't do in that picture is put it together and show you the actual hypercube or tesseract. When you think about it, a three-dimensional object is really, on paper or the computer screen, a two-dimensional representation of a three. To do a tesseract, we'd need a two-dimensional of a three-dimensional rep of a four-dimensional object. So I think we'd lose a lot in translation, which is why we end up with the exploded views as opposed to the assembled views of the tesseract. But if you Google online tesseract, you should be able to find exploded views rather straightforwardly.
Interesting. So Nick tried to clarify his question. He says, by my understanding, which is limited, the cause of the time dilation, such as a high gravity field, would move into the wormhole, creating a gradient over the normal range, the source of gravity.
You know, I have never thought about that. And I don't know if anyone else has. You may have come up with something original. Congratulations on that account, if that's the case. But when everything I've ever read, including Matt Visser's incredibly outstanding treatment of wormholes in Time Machine, which is probably the most, even though it's not totally up to date, it's the most comprehensive there is. That second book is highly technical for the most, even though there's survey articles on wormholes and warp drives, highly technical. Most of it is application of the energy conditions, which I didn't have time to get into, and how they constrain relativity and how they constrain wormholes and warp drives. And then the bottom three books talk about various aspects of this in much more understandable terms. But in no treatment I've ever looked at, including recent paper, the Wormhole Revolution is truly a revolution, and so is the warp drive revolution. It's ongoing, and every year on archive you can find a slew of papers in wormholes and a slew of papers on warp drives. So what Kip Thorne started with wormholes to this day is ongoing. Well, Kip Thorne and Michael Morris and Carl Sagan started. It's ongoing.
I'll to write a screenplay.
Yes.
For a story.
Should
Jeff
I
says,
say it's gone viral?
Yes. Jeff asks, it would take time to construct or adapt the wormhole to time travel. There would be the usable lifetime and then the decay of the wormhole. Any idea how much usable time there would be compared to development and decay times? It's a lot of thought experiments going on here. But
part of the problem is to create a time machine in this way. You have to go for a while at a considerable velocity and then come back, which is part of the overhead, or bring it out to a wormhole, let it go in orbit for a while, and then bring it back. So that adds to the time. And I guess the question is, how far can you stabilize a wormhole to where some perturbation eventually undoes it? Can you be absolutely perturbation proof? And I really don't know. You might be able to actually tune up a wormhole as the throat starts to shrink, infuse it with more negative energy or more exotic matter, bringing it back to the original size of the throat. So it might be possible by periodic revitalizations, but now I'm talking off the top of my head, by periodic negative energy or exotic matter revitalizations to tune it up when it's gone too far beyond what it started as. Well, and maybe someday there'll be wormhole mechanics who do wormhole tune-ups. Who knows?
As Doc Brown said in Back to the Future, we've got all the time in the world. We have a time machine.
Yes. Well, a line I remember from the classic sci-fi movie Forbidden Planet. It's not a line. I guess it is a line. There's someone there who's dealing with the damage klystron modulator, which they need in order to short circuit the space-time continuum to contact Earth from Altair, whichever, Altair 4, Altair 5, I forget which planet. But anyway, he says something like, this is just a paraphrase, any quantum mechanic in the Space Force would give their right arm to get a hold of one of these. Right. So apparently at that point, quantum mechanic was a profession or even a trade.
Tony asks, did you mention what the energy requirements were for a, quote, reasonable wormhole based on a list of criteria that you provided?
Okay, originally they had things like galaxy-sized massive exotic energy, then Jupiter-sized mass, and warp drives also had similar things. And they kept, Matt Visser did wonders in getting them. He has some metrics. Not all of these have been analyzed to death because he came up with a profusion of wormhole types, including planar wormholes, where the mathematical version is you identify two, say, rectangles, so that as you walk into one, you simultaneously exit the other. And that's a lot, or they could be circular, and that's or whatever, that's a lot closer to the conception of a Stargate. But anyway, some of his types used arbitrarily small amounts of exotic matter, which would seem to imply almost any amount could do it, but that would require quite a bit of analysis. And I want to say one other thing about this. You might get to a regime where quantum gravitational effects are important, and if that needs to be taken into account, we don't have a quantum theory of gravity. The best we do right now is semi-classical theories, where we use quantum fields on a classical space-time background. By classical, I mean general relativistic, but non-quantum. And we can do quantum mechanics in curved space-time to a certain extent, but we can't do full quantum gravity where the gravitational background, the space-time itself, is treated as quantum. And it might be that just as in, there was talk of wormholes with two horizons. The ordinary Schwarzschild has a single horizon. You go in, you can't get out. But some wormholes, like rotating and or charge, have two horizons, an inner and an outer. So you go through the outer, signs of terms flip, and you can't help but be drawn to the center because the roles of radius and time have interchanged. So now going to shorter distances is like ordinarily going into the future in time. So you can't help but be drawn into the singularity. You cross the second horizon and space-time becomes normal, so you can turn around and leave, except you can't reemerge through the second horizon. So it turns out what you're looking at is only part of the wormhole solution, and there's a maximal solution called the maximal analytic extension, and it contains many wormholes in case or black holes, in fact, an infinite chain, and also white holes. So you emerge through a white hole and find yourself in another universe that's not the one you started, and then you look and see a black hole, but it's not the one you entered, and you play the same game and go to a third universe, a fourth universe hopping. So if the classical solution holds, black holes with two horizons might be wormholes in effect, but quantum effects might prevent that, and there's good reason to think that. And semi-classically, we could already find problem, but until full quantum gravity comes along, we won't know if any of these wormhole, black hole, warp drive, whatever technologies might have flaws that we're not seeing now.
That's cool. I put up Howard Blair shared an image of a 2D visualization of a 4-dimensional cube. So that's
is it possible to somehow make my, oh, there it is. Okay. I was still stuck in the presentation trying to upload, and it seemed to just be cycling, but now I got rid of that. Very nice.
Thanks, Howard, for sharing that.
Okay.
Any other questions for Dr. Brighty? Fascinating talk. Fascinating talk. And I'll give a plug. I know Steve would probably do this, but I'll give it. If you haven't been to the planetarium lately, there is a show running called Black Holes Revealed. And it's a really good show. It talks a lot about black holes, and Steve does a good job of explaining a little bit about wormholes and the instability of connective wormholes forming and all that. But very fascinating show. So I highly recommend seeing that while it's still around at the planetarium. And you do need to make plans ahead of time to do that, because the shows sell out every time they're on. And the planetarium is open Friday, Saturday, Sunday. So take a look online if you want to go see one of those shows. It's worth your while.
Sounds interesting. Thank you. By the way, I want to apologize again. I totally lost track of the time.
Not a problem.
This is a topic I just get totally lose myself in. I've given similar wormhole talks. I mean,
That's awesome.
warp drive talks.
Yes. Yes. Thank you very much. Very interesting talk.
Oh, you're quite welcome. I enjoyed doing it. Hopefully, we didn't lose too many people because of the length.
No, you were. I appreciate the. You were able to keep the math brief, and you're able to explain it a lot physically versus making it all numerical. But the numerical part does help to balance, what you're seeing in the equation. So appreciate that. It was a lot more understandable.
For future purposes, do you think explaining what a space-time metric was unnecessary? Because that took a little bit of time to go through.
I think that was important. It was important to understand what you were talking about.
Okay, thank you.
Other questions? Dave Bishop says I needed that.
Oh, okay.
Dave's a very technical person. He actually runs our supernova page.
Oh, neat.
All right. Any other questions? Thanks so much again, Dr. Brighty. Appreciate it. This is a great talk. I'll open it up. Anybody wants to chat, talk, whatever, you're welcome to turn on your camera, shoot the breeze a bit. I'll close the presentation. I'll put my camera on.
This is Dave Bishop. During some of the questions phase, I was going over some of my slides for the next talk. I've got 70 so far. And
so this is for next month, for June, the astronomy year in review. That's moving a pretty good clip. That's a couple hours. If you spend a minute and a half or so on each slide, that's a lot. Good stuff.
Well, that's the problem with it. I mean, there's so much that happens on a yearly basis.
That's great.
Including some really weird things that have happened with some of our space probes.
Interesting. And that could be some of this, moving through space at different distances from other masses. Yeah, that's interesting.
One of the weird ones that actually got talked about by NASA was the Juno space probe. The Juno space probe locks on to Earth via an FM signal from the Deep Space Network.
Okay.
It accidentally locked on to Ganymede. It actually got a 2-minute FM signal lock on Ganymede. Now, I can understand an AM aurora, but FM?
Yeah, and for 2 minutes.
2 minutes.
2 minutes. It's not like it was just a couple of seconds or nanoseconds. Wow.
Right. It's stuff like that it's news. It happened. You can look it up. I've got the articles. NASA admits it happened. But I mean, what plausible thing could be happening in Ganymede that would produce FM?
Well, it's the agricultural colony there that's trying to get back in touch with Earth.
Oh, that's right. Robert E. Heinlein, Farmer in the Sky.
That's right.
How can I forget that? Considering I read that book back in the 1960s, it should be there by now, right?
You're right. I'm surprised you got the reference. That's awesome.
No, I've read too many thousands of science fiction books.
Yeah, that's great. That's great.
No, that's one of the things that I'm going to have in my talk. Just one of the little tidbits of interesting kind of things that happened during the year that happened. They just kind of escaped the media.
Yeah. Yeah. The media likes a lot of sensationalized stuff. And even though that's pretty sensational, it may have been a little more esoteric that people wouldn't understand. Interesting.
Okay. I just thought I'd give myself a little ping there.
Gotcha. You're plugged. You're plugged for June. Awesome. Thanks, Dave. Okay. If you haven't watched the movie Interstellar, go watch it. It's a pretty interesting story. Kip Thorne is a pretty reputable person with his support, and he's very close on the logic of what's happening, even though it's theoretical physics. It's pretty interesting what he does, and it's great. It's good acting. It's actually a good all around movie. I saw it when it came out. There's a bunch of us that actually we together went to saw it in IMAX over at Tinseltown in Gates when it came out, and it was well worth seeing it on the big screen. It's one of those movies. Any space movie is great seeing it at IMAX, and that ended up being a really good time for all of us there. And Tony says Ganymede was also an agricultural planet in The Expanse. Yes, and we're waiting for what season? Is it season 6? What is it? Yeah, we just finished the season. That's a great series as well. Anybody else here watch The Expanse? Kind of between seasons right now. They just finished the last recordings of the last season. I think it's within the last couple of months anyway. I think it was November, December, something like that. Great stories. That's actually a book series as well, if you're into the science fiction.
Yeah, I mean to read those books. I'm actually going over some books by Robert Hamilton, which is in his science fiction books. You travel from planet to planet by train through wormholes. So you start on Earth, you get on a train, it goes through a wormhole, it goes through another wormhole, and they keep on going out into the galaxy.
That's pretty cool.
That is cool.
That's an expensive train. Mark
Robert
Dudley has
F.
a question.
Hamilton is the guy's name.
What's the guy's name?
And the book series is called Pandora's Star. Is the first book.
I think I've heard of this. Hamilton. Okay. Mark Dudley has a question for you, Donald. It says, are there any writers other than Kip Thorne who are reputable authors of explanations of these topics? We all miss Carl Sagan. Actually, Mark, did you catch the end screen? There were a bunch of books that were there. Let's see.
There are several popular ones. Enrico Rodrigo wrote a book called The Physics of Stargates that does an excellent job of, among other things, of summarizing progress in wormholes that happened since the book Lorentzian Wormholes was written. And quite a bit has happened. Tom Roman, who was in the Relativity group at Syracuse University, a colleague of mine in graduate school, together with Alan Everett, wrote the book Time Travel and Warp Drive, and he's the Roman of the Roman ring. He came up with the counterexample to Hawking's chronology protection conjecture. And then there's lots of technical people. For instance, Francisco Lobo, who wrote the second of the upper books, unfortunately it's exceedingly technical, is an active researcher in the area of warp drives.
Good stuff. It'll be on the recording when you want to look at it later.
Right. And I know there are more recent books that I haven't even had time to look at, because I don't necessarily keep up with all of the popular level books and something, but any of the bottom three, although one thing I would point out, the Science of Interstellar, while it has a lot of good things, is geared to the movie. So it discusses several different topics. If you just want to focus in on Wormholes and Warp Drives. The first two books on the bottom are good ones. And Time Machines.
I have a poll I'm putting up. Are you going to watch Plan 9 from Outer Space now? I spelled outer space wrong.
Have you seen the movie Ed Wood?
I've heard of the movie. I don't think I've seen it. No.
Yeah, who of course is the director of Plan 9. He's done some other movies that are equally bad.
What's
Some people,
Go ahead.
some like to say so bad that they're good, but I wouldn't go that far. Have you read The Three Body Problem?
I haven't.
There
Anybody
is
else read that? Go ahead. Go ahead.
There's a trilogy of books by the Chinese science fiction author Cixin Liu. I think it's Cixinliu. And the first one is The Three Body Problems. And they fall into the genre of hard science / hard engineering, which means they're very well based on physics and in some cases engineering, and quite an interesting trilogy.
Sounds it. Sounds it.
It's a first contact novel.
Yeah.
And first contact, not necessarily to our benefit, but I won't say anymore. But and it's done by a Chinese researcher. I teach a course in the science of science fiction, and one of the things that comes up whenever I mention METI as opposed to SETI, messaging extraterrestrial intelligence, which has already been done dozens of times. You had the plaque on the Pioneer probe, you had the golden record on the Voyager, you had the Arecibo message, Russia had Cosmic Call 1 and 2. I think it was Europe that did something called Across the Universe, where they played the Beatles song along with a bunch of messages. There's something called the WOW reply, where the famous WOW signal in the direction is said, where I like to say, if you wanted to prove to aliens that there is no intelligent life on Earth, beam 10,000 tweets into space, which is what was done.
Yeah, that's pretty much solidifies things.
Yes.
So here's our results. It looks like a third of us are going to go watch Planet 9 from Outer Space. A few people know, and a few people abstained. So that's who was left anyway. So, well, thanks everybody. Appreciate you guys coming out tonight. Thank you, Donald, very much for your talk and sticking around
I
for
wish
questions.
I could have kept it within the limits.
But you're fine. You weren't. We had some technical stuff that kind of threw things off. So you did fine. You did fine.
Okay, well, I enjoyed it. Thank you for the opportunity.
Thanks very much. Good night, everybody. Appreciate everybody being here. Thanks.
Thanks. Good night.